So in this video, we will look at the X, Y, Z, and H buttons. What are these? What are these gates, and uh, what they do? What is the mathematics behind them? What are the basic states? What is direct notations? All of that in this video. Uh, so let me just clear this first. So let me go to the Qiskit documentation. So this is the textbook of Qiskit that introduces you to some of the basic things from basics up to the advanced things. So what you can see here, this is the X gate. So note that all the gates you see, uh, as you can see here, all these gates are actually denoted by a matrix. All of these gates have their own unique metrics that denote them, and I can minimize this. So similarly, this X gate is denoted by this matrix, this 2 by 2 matrix, 2 cross 2 matrix with these 4 entries. This denotes the X gate. So uh, initially, a qubit is in this state. This is called a ket, zero ket, and this is just this vector. So so this and this is the same thing, but the way of writing is different. So this is how you write this vector in the direct notation. These are called direct notations. So this is called 0 ket and this is called 1 bra. So this is the bracket notations, or uh, the direct notations as we say, and these actually these 0 ket and 1 ket form the basic states. This is the states in the computational basis. So this is think of it as a computational basis is on the z-axis. You will see shortly. So let me just click this X and visualize. So it started here in 0 ket that you saw here, this vector, and it should end up here according to this mathematics. Should end up here. It ends here. So when you apply X gate, it transforms this 0 ket into this 1 ket denoted by this direct notation. So this is also simple vector with 2 entries 0 1, and the other one was 1 0. This was 0 ket and this is 1 ket. And what happens is when you apply X gate to 0 ket, initially every qubit is in the 0 ket in that state in Qiskit. So when you just start your function, initial state is here. This arrow this is pointing here, and when as soon as you apply the X gate, that transforms that vector into the 1 ket, and this is the driving mathematics. Simple matrix multiplication. The only takeaway is this matrix that it denotes and this operation. So you should ask me what happens when I apply x to 1. It will be the converse. So let me just show it. Let me just close this and clear. So when I apply x once, we now know that it will transform the 0 ket state to 1 ket state. So let me apply this again and see what happens. So I will visualize. See, it's applied, and let's see what happens. So previously it stopped here, but this time it won't. And let's see where it goes. And see, it gets back here to the initial position. So what it means? It means that when you apply X to the 0 cat, it transforms the state to 1 cat, and when you apply the X gate to 1 cat, it transforms it back to the 0 cat. So that's why we call it the uh, bit flip gate. So if I show you, flips the state of a qubit, and this is the command that we use uh, for it, just .x. This circuit is the instance of quantum circuit class, and we will see what is this class later in one of the videos. But realize that this circuit just denotes the quantum circuit, and we just apply X gate. So this is the entire command that you use to apply X gate in Qiskit. So let's close this. Let me clear. So we are back in the initial state now, and this is the symbol in Qiskit that you can see. So you can see it here, and as expected. So that's just what we saw. So let me apply Y, and let me visualize what happens. So it's going, and it stops. It stops on 1. But realize that the plane of rotation was different in the two cases. Let me show you again so you can keep a watch this time. When I apply X, see the plane rotation is perpendicular to X axis, this plane, right? And okay, we are done. So I'll clear it again. I'll apply Y and I will visualize. This time we are moving in a plane perpendicular to the Y axis. So whenever you apply a gate, X or Y or Z, the rotation happens in the plane which is perpendicular to that axis. So again, we ended up in this one state. Let me show you the mathematics that drives it, Y and Z. So this is the matrix that denotes it. This denotes Y and this denotes the Z. Let's keep Z apart from for a moment. Uh, Y gate is denoted by this, and it will also end up in the different in the one cat. But you can see here. Let me just scroll a little up and see there's the difference in this denoting this X gate. So this is how you express it in another format. It is the same matrix but being expressed differently. And if you see by, there is a difference in the way of representing. We have this I here. This is called relative phase. We'll see that, and you can think of this as a sort of reason that differs. So you can see here we don't have one, we have minus I and I. We have complex entries here. This I denotes the complex numbers. So complex number is A plus IB. So A denotes the real part, the real number, and plus IB is denoting the imaginary part. So B is the imaginary number. But both of them actually are part of this state. So you can see X was denoted by these all the real entries. We had the 0, 1, 0, and 1, 0 entries. But here we had complex entries minus I and I. So this can be thought of as a reason why the rotation was different and why X and Y are not the same gates, though they end up despite the end result was one cat. So again, let me get back here. Let's see what happens when I apply this two times. Let's see. 1. Here we know that would happen. Again, going up. it should be 0. So again, we see that the same thing happened. It again got back to 0 cat. What happened by applying x gate twice, but the rotation was different, and x and y are therefore not the same gates. So I'll just close this, clear this, and you can see this Z gate. Again, this is the difference, right? Now, if I apply a Z, the rotation should be perpendicular uh, in a plane which is perpendicular to the Z axis. So let me see if something happens. Nothing happened. Why? Because it's not possible to move in the Z in this plane perpendicular to Z axis, because this is the Z axis that you are seeing. So we first need to get into the into this plane if you want to see Z in the action. So let's keep Z aside and talk about another gate, the H gate, denoted here, also known as the Hadamard gate. So Hadamard gate is denoted by this matrix, and when you apply to 0 cat, it ends up in plus state. What is this, we will see. And when you apply it on one state, it will end up into this. So let's see what is this plus and minus state. Just a second. So initially our circuit is in the 0 cat state, we know that. So let's just apply this, then we should end up in the plus state, plus cat state, you can say. Visualize. See, we are moving here, and let's see where we end up. So this state that you can see here is called plus state, and is actually a superposition of 0 cat and 1 cat. So it half 0 cat and half 1 cat, as you can see here, right? It's in the midway of both the states. And also realize that now we are in this plane, Z plane, in the plane which is perpendicular to Z. So now if I apply a Z gate, something should happen for sure. So let me close this again, and let me clear this. I apply H, I apply Z, and now something should happen. So we know that it will end up in the plus state here, nothing surprising. Let's see what happens next. And now you see the rotation is happening. So this is how Z gate works. So I hope you got a good visual understanding of these gates. So the rule of thumb or the takeaway is that the rotation will happen only if the state is in a plane which is perpendicular to that particular axis. And these gates just make a x, y, and z rotate the vector if it's in a plane perpendicular to the respective axis by pi radians. So 180-degree rotation. So applying twice gives you 360-degree rotation, and that's why you end up on the same thing where you started. So if you apply on 0 cat, you apply x twice, you end up where you started. And that's the reason, because a 360-degree rotation will definitely make you land where you started in a sphere. And what is this sphere basically, that you might think? This is a Bloch sphere, and this is a way of denoting the states of a qubit. We will go into details later, but think of it that this vector, that you colored vector that you are seeing, is just denoting a state. This is the state of the qubit right now. So, and it denotes how the transformation is taking place for that particular qubit. So I hope you like this video, and in the next video we will see these remaining gates. Rx, Ry, Rz, S, Sd, T, Td, and what do they mean, what do they do, what is their functions. We will see that in the coming video, and I hope you have understood what are X, Y, Z, and H gates and how do they work. If you think you have not understood the mathematics deeply, so it's okay. I'll be trying to come up with a series where we will just focus on the math. But here you know something yet, like how these rotations happen. And once you complete these series, this series, first series, you will be having a tool that will help you to experiment. So you can just freely visualize whatever you want on the block sphere, and we will go into the details of quantum mechanics later after we complete this series. So so it will be you will be able to visualize everything much more easily when we will talk about math. And I know we have talked about math in this video as well, the various metrics, and it was just simple matrix multiplication, but we will go much more depth into much more depth in the a separate series on quantum mechanics, where we will talk about the different phases and what are density matrices, what are various, we will talk about various quantum algorithms and some interesting uh, stuff. So I hope you stick to the channel in this series. You also come back for the other series. Uh, so that's it for this video. I think this video is pretty long. So I hope you like this visual representation of all the single qubit gates. Thank you very much for watching this video.